Okay, so thanks. First, I want to thank the organizers to give me the opportunity to present this work. Actually, I want to apologize to 2 or 3 people in the audience who already saw this talk exactly in the same room 2 months ago. I changed a few things, actually, because when I presented this work 2 months ago, there was only statisticians in the audience, so I made a lot of terrible jokes about people in optimization theory. And actually, today, I removed these jokes. Actually, because I have to be honest, I know nothing about optimization theory. And still, I wanted to talk about it. So, I mean, the reason why, and actually, it will explain the reason for this work, actually. The reason why is that I come from a different community. So I come from the community of people working on aggregation of estimators. And in this community, well, there are many theoretical results. There are also people using Monte Carlo methods. And when I talk about either theory or Monte Carlo methods to people like you, I mean, people who know about optimization theory, they usually expect that I'm not able to implement anything from the methods I'm talking about. And in some way, it was true. But I mean, the object of this talk, the purpose of this talk, is to prove that actually some prediction methods in aggregation theory can be approximated using variational approximations, so using actually optimization theory. And even if I don't know a lot about it, you can imagine by yourself that actually you can use very powerful algorithm to implement these methods, actually. So I'm going to start by a short introduction to aggregation theory, and then by a theoretical analysis of variational approximations, so of, in some way, optimization theory for aggregation theory. And so, yeah, first, aggregation theory, and it will be a very, very low-level introduction to aggregation theory, so you might know already a lot, but I'm sorry, I have to keep the slides at a level that I can understand myself, and it's a kind of challenge. So, I should not say that, actually, because this talk is being recorded, so some of my students can have a look at it in a few days, so maybe we'll remove the first 3 minutes before it's published online. Okay, yeah, so just a motivation for aggregation theory, and like actually for learning theory, okay? So you have a sample and you want to learn from it, but you don't want to write likelihood, so you don't want to do like traditional statistics, you know examples, you've already seen these examples since 25 years on the web, so you know that you can learn something from these data sets, but you don't want to write the likelihood. And so what you have, what you usually have to choose in order to deal with this problem, you have to choose a few ingredients that are recurrent in all the versions of supervised learning. You have to, well, you have observations first. So actually, I will deal with object labels problem. So X is the object, Y is the label. Actually, I will present result in the batch learning setting and in the online setting as well. But in any case, I will stick to the same notations. And then you have to define a set of predictors, linear predictors, kernel, anything you want, okay? So I will use this notation, f theta, it's indexed by parameter theta, which can be in a finite or infinite dimensional set theta. F theta, of course, is meant to predict y, and then you have a criterion of success. So obviously, I will define accurate notations later, depending on whether we work on the batch setting or in the online setting. But basically, you can think of something like, well, in statistics, people tend to use things like that, but I will more focus on prediction-related criterion, like, for example, the out-of-sample prediction accuracy. So this would be for a classification problem. Obviously, I will deal with more general problems, classification regression later, but you can keep this in mind. So we want a criterion. What is a good prediction? What is a good predictor theta? And finally, we'll use, in many cases, an empirical proxy, an empirical approximation of R, which I will denote by small r. And for example, you can think of the empirical risk that you want to minimize. So basically, this is all the ingredients that we need to be able to talk about something in learning theory. And actually, in aggregation bonds, so-called packed Bayesian bonds that I'm going to present right now, you need one more ingredient. It's a way, well, actually, you need that. You know that in some way you need some assumption on the set of predictors. You need to control its complexity. I mean, not even in order to do some optimization, but just in order to relate in some way this theoretical criterion of success and this thing that you can observe. And in order to relate this to this, you usually need an assumption on the set of parameters. And in aggregation bound, usually you replace this by a prior probability distribution on the parameter space. Okay, so it will be used in some way to replace the complexity measure like Vapnik dimension on the parameter space. Okay, and all the bounds I'm going to present today take they look like that. Okay, so you will have a bound on the average prediction risk, and it will be upper bounded by a bound which is a balance. So you're probably used to the bias variance trade-off. In this case, you have a kind of slightly different trade-off. Actually, you have an infimum over all the possible aggregation distribution, and this time you have a balance between, well, this term, which would be actually the best possible prediction. And in some way here, you wouldn't want to take really a probability distribution. You would just like to take Dirac mass at the best possible parameter. Okay? But on the other hand, you have like a variance term. And here it is actually the Kullback divergence between the aggregation distribution and the prior. Okay? So in some sense, it will replace the complexity measure that you have in, like, for example, in Vapnik bounds, in the sense that, well, obviously, as I said before, you want, in order to keep this term as small as possible, to choose rho as a distribution that is very, very spiked and concentrated around the best parameter. But on the other hand, when you concentrate rho around a single parameter, the Kullback divergence with respect, for example, to a uniform prior will explode. Okay? And how fast will it explode? And usually it's related to the dimension of the parameter set theta. Okay? So here you will have the usual balance between good prediction and complexity. Okay, so obviously this bound is just like I didn't say anything about, well, what is this small o? So is this small o of 1? I mean, does it depend on the dimension, on the sample size? Actually, I will give precise bounds later. So just accept that there will be additional terms, but that's what you need to understand the bound is these two terms. Okay, and actually, the other good news is that usually, well, depending on the bound, it will hold for a large class of aggregation measure. But actually, very often, the one that we want to choose is this one, because some bounds are valid only actually for this probability distribution, this aggregation distribution. And you can see that it looks, I mean, if you're familiar with Bayesian statistics, it really looks like a posterior. Okay, so you have the prior multiplied by something that gives weight, more weight actually to parameters that make good prediction. Okay, so if you see this as a kind of pseudo likelihood, then you can interpret this as a posterior. Okay, if you prefer, you can see it as a kind of smooth version of empirical risk minimization, because obviously we'll give more weight to parameters with a small empirical risk. Okay, it's clear?
So you call this rho thing the aggregation measure?
Yes. It's not, you don't like the term aggregation measure? Okay.
I'm not familiar with the terminology, that's why I'm learning.
I mean, I would call aggregation measure any measure on the parameter space, actually. So the thing is that depending on the papers for this, okay, sorry. I will call aggregation measure any possible rho, actually. Because I will replace this one by a more convenient one later. But depending on the paper, actually, you have many different names for this one. In Bayesian statistics, people, well, they don't really like that because it's not a likelihood, but still they use it and call that a pseudo-posterior. My PhD advisor, Olivier Catoni, called that a Gibbs measure. And finally, you have the exponential weight averaging because of the exponential weight that is used a lot as well. So it depends on the paper.
So how do you relate this aggregation measure with the, if you go to the previous slide, to the standard setup of prediction in machine learning?
Yeah, so actually it will depend on the result that you use. Sometimes, I mean, when the risk is convex, oh yeah, I mean, I talked to people doing optimization, so I had to use the buzzword convex at least once. I did, thanks. When you use a convex risk, actually what you will do is simply use Jensen's inequality here and actually try to lower bound and just lower bound this by the risk of the aggregated estimator. So in this case, actually what you want to do is to compute a posterior expectation, okay? On the other hand, when it's not the case, when it's not convex, you can see that this is still a bound on the procedure, but this procedure is a randomized procedure that will, at each time that you're given a new object x, it will draw a parameter theta according to this probability distribution. and then you predict y as f theta of x, okay? And then this is an upper bound on this randomized procedure. So it depends. I mean, if the risk is convex, you can relate this to an aggregated parameter. Otherwise, you have to use a kind of randomized procedure. But in both cases, you have something practical. I mean, practical if you can deal with this. And this is what I'm going to talk about. OK, so I will present you actually two more accurate versions of this bound, depending on the context. And the first one actually is a bound for batch learning. So you have a given sample. IID, well, IID actually the independent part can be removed if you have some assumption on the dependence between the observation, but just for simplicity, yeah.
Can you go back one slide?
Yeah.
There is no small r. The bound is not with small r, or it is big with a big r.
I mean, okay. I can provide you, and actually I will later. I can provide you a bound with the small r here. But here, in some sense, it will be like a kind of empirical bound, the one that you can compute on the data, and you can know that your probability of error is smaller than 0 point something. Okay. Here, I'm more interested in this kind of inequality where actually you want to be sure that, I mean, even if you cannot compute this bound, you want to be sure that in some way you will be very close to the minimizer of this quantity. Okay. But actually, both are related.
Your posterior is the minimizer of that one with...
Exactly. I will come back later when I present the proof, but it seems that you already guessed how I'm going to prove the result. So, yeah. So, an IID sample from a probability distribution P. Well, the set of parameters, I have nothing to say about it. It can be anything for the moment. And a risk that can be written as the expectation of a loss function. And for the sake of simplicity, even though, I mean, it's not necessary. I mean, this kind of bound can be generalized to unbounded loss functions, but for the sake of simplicity, I will present one of the weakest versions of these results for a bounded, actually, loss function. Okay, and finally, well, the empirical risk is then obviously defined in this way, and you still need a prior pi, but for the moment, I don't provide an explicit form. And in this case, you have the following result. So it's a pack bound, okay? It's valid with large probability, and it says that the risk of this exponentially weighted aggregation procedure, whether it's randomized or whether you have a convex loss and you use then the posterior expectation, well, it's upper bounded by this, okay, this term I promised you, okay, the balance between a good, I mean a small value for the theoretical risk and then this complexity term. And then the reminder that you have is, well, obviously a log of 1 over epsilon as it's with large probability. And then this lambda times b squared over n, okay? Where actually I remind you that b is the upper bound on the loss function. Okay, so actually this bound is due to Olivier Catoni, but actually it's based on previous work by John Cho Taylor and David McAllister. And I just want to explain, I mean, obviously it looks like what I promised on the previous slide. But on the other hand, maybe it's not very explicit. So I just wanted to, I'm going to provide many examples later in the talk. But I just want to provide one example in a very simple case where actually the predictor set, so theta, is a finite set. And just to check what happens in this case, okay, what this term and this term look like, okay? So just assume that you have a finite set of predictors, and then I'm going to do something quite simple. I choose the prior as a uniform distribution, okay? Then, obviously, you have this bound. Actually, it's just the same bound as in the previous slide, but if you don't want to calculate something too complicated, you can replace, actually, the infimum over all probability measures, but the infimum over all Dirac masses, okay? And then, obviously, the integral of the risk in this case is just the risk of the parameter theta I. And then, actually, you can compute the Kullback divergence between a Dirac mass and a uniform probability measure on the finite set. I think it's feasible. And then, well, actually, it's the log of the cardinality of the set. And then you can see that, well, this bound, remember that it depends on the parameter lambda, the one in the posterior. Oh, maybe I should come back here. This one here, actually. And in case you don't know how to choose it, now you have a way to choose. You can try to optimize the bound, and you obtain that actually your aggregated estimator performs as well as the best predictor plus this term, square root of log m over n. Okay? So without any other assumption, well, I'm sorry, the optimal choice for the parameter lambda is given here. without any assumption on the loss function, actually, you cannot improve on this. If you do reasonable assumptions, for example, when you use least square, the least square estimation, so actually you use the quadratic loss, obviously you can improve on this. So there are refined versions of this bound. There are many, actually, in Olivier book, you have probably 156 different versions of this bound. Some of them don't include one parameter lambda, but 77 parameters, lambda 1 to lambda 77. But in the end, you have bounds, for example, for the quadratic loss without the square root here, which is, once again, the optimal rate. Okay? So it just gives you an idea of actually what you usually do when you have a prior and a set of predictors. Usually you try to upper bound this by just not taking the infimum over all probability measures, but actually over a suitable set of probability distribution that you can actually deal with, I mean, in the computations. And you end up with a prediction bound, which is usually, if you do the calculations quite well, you will usually end up with something that is not too far from being optimal. Okay. I want to present the same bound, but in a different setting, actually. So in online learning, so as promised, I use the same notation, but this time I don't have any assumption, actually. So maybe the uppercase later in this case is not very well thought, because the xi, yr are not meant to be random variables. I deal with online setting, and any possible sequence, x1, y1, it can be obviously generated by any algorithm, even by an algorithm which knows actually which aggregation procedure you are going to use. But anyway, you have the same setting, a set of parameters. In this case, I will focus on the regret. Okay, so it means that at each step, I'm going to use xt and the previous observations to predict yt by, say, yt hat. And then I want to compare my accumulated loss to the cumulated loss, of the best possible predictor. Okay, so I use still the same assumption that the loss is bounded. Once again, it's something that you can remove with different assumptions, but I want to present once again the simplest version of the bound so that you can compare with the previous one. Okay. And then at each step, actually, you can still use, you can still have a kind of proxy of the quality of predictor, okay, which is the empirical risk up to time t-1. Okay? And the prior, but once again, I will give a general version, so no assumption on the prior. So here what I propose is to do basically the same, but at each step t, okay? So at each step t, I define this exponentially weighted aggregate. Okay, so the prior multiplied by exponential to minus lambda times the empirical risk at time t. And then I use as a predictor, and in this case, you can see that I use the convexity of the loss function. So actually, I don't use the randomized procedure, but actually I could have, okay. In this case, I use the aggregated predictor, okay, under this pseudo-posterior distribution. And then you have this result. So actually, I'm not really sure who was the first person to write this result. You have a version in Cesabianchi and Lugosi's book with a discrete parameter space. But actually, I found a very clear explanation about this result and many, many variants in Sebastian Gershinowicz's PhD thesis. But I don't know if he was the first one to write this result under this form, actually. So this time, the cumulated loss is smaller, and you still have this balance between, well, the best possible aggregation, but you have to keep, once again, this complexity term, so the distance with respect to the prior. Okay? So you see that in some way things will be almost the same. I mean, if you specify a prior pi and a parameter set theta, then you can then choose optimal, I mean, you can explicit this term, and then you can choose an optimal parameter lambda. So, I mean, basically it's the same, for example, if you use a finite parameter set, so I don't want to do all the calculations again. Okay, so now the remaining of this talk will be about, well, are you sure that you can compute this? Okay, so I think that is quite important. I discovered that this kind of thing can be important quite recently, but even though, I mean, I think it's quite important. Before that, I have a few remarks about these techniques to do in order not to upset anyone in the audience. First, you have many, many other versions of this aggregation bound. So a very famous one is a version by Dalalio and Tsibakov The difference is that it's not exactly on prediction, it's on estimation, regression estimation with fixed design. So you cannot really give something about prediction risk, but on the other hand, it's very, very convenient because they have no boundedness assumption, so it's very, very convenient. Their tool is very, very convenient in many settings. And there are other links. Actually, they used in their paper a lemma by Lung and Baron, but you have many, many related things in aggregation theory and statistics which are not exactly the same kind of bound, but still are very related to this approach. Okay, and something else, there is obviously a relation for those among you who are statisticians and who know about Bayesian statistics. Obviously, there is this link I mentioned with Bayesian statistics. If you see this as a pseudo likelihood, and obviously pi. I call it the prior, actually, and I call it a prior because there is this link with Bayesian statistics. And there's been a few papers recently where people motivate the use of this probability distribution, even when you're not doing statistical learning, just when you're doing Bayesian statistics, to use something like prior times a pseudo likelihood. I mean, you can think of an example, just for example, this is just a short parenthesis for statisticians, but for example, if you have Gaussian observation and you try to estimate the mean, then here, obviously, you would use a Gaussian posterior, so actually it will be the same, but the risk here would be the quadratic loss. Okay? But in practice, when you have outliers, you know that the quadratic loss leads to non-robust estimation. So for example, here, they propose to replace it by a robustified loss function. Okay? And in this case, you don't use here the likelihood, but still, you have something that looks like this decomposition, prior and pseudo likelihood. So you might have other reasons, even though I believe that the one I presented before are the best, but you might have other reason to use this kind of pseudo posteriors.
When you say pseudo likelihood, so if R is a negative low likelihood,
then it's exactly a likelihood. The reason why I call it pseudo likelihood is that usually when you mean likelihood, you mean that you describe a parametric distribution on the observations, which is not the case here.
The Bayesians are not allowed to choose lambda.
Bayesian are not allowed to choose lambda. And actually, in all my theoretical results, I choose lambda in a way that would not be acceptable by Bayesians. So I agree, it's not exactly the same thing, even though it's close. And just one last thing that I usually like to mention is that there is a community in Bayesian statistics of people who like to analyze the rate of convergence, the concentration rates of posteriors. And it's quite funny because they use completely different tools, but in the end, they usually end up with the same computation. What I mean is that when you compute this bound here, usually you have everything that is needed just from a technical perspective, even though the proof is different, but you have everything that is needed to use, for example, this kind of tools to compute the concentration of posterior rates. Okay, so sorry for the parenthesis, but now I'm coming back to the main purpose of this talk. So actually, the problem is we want to compute this. And when I say compute, what is to compute a probability distribution? Well, I mean I want to sample from it or to compute the mean. Okay. Obviously, if you know about computational Bayesian statistics, you know that there are methods to do this. There are Monte Carlo methods. Okay. So for example, actually in the paper by Arnak and Sacha, this is what they do. Actually, they propose the Langevin Monte Carlo algorithm to compute their estimator. Well, I did a work with Gérard Biot, and we used the reversible jump algorithm to compute our estimator. So actually, there was an attempt to use Monte Carlo method for this, but this is where actually the dark side and bright side in the force comes in. I mean, when I present MC method in front of optimization theory people, usually they tell me, "Ooh, dark side of the force, you shouldn't use this, it's too slow." And I mean, it's not only that it's too slow, because in some cases it works well, but we don't have guarantees on how far are we from this quantity, okay? So I want to say that it's not completely true, and I want to mention these two papers presenting different approaches. I mean, this one presents concentration inequalities for Markov chains when you start from the non-stationary probability distribution. So in some way, you have a tool to prove a concentration of the empirical approximation that you get from an MCMC. On the other hand, it depends on many assumptions on the Markov chain. And to me, it's not clear how these assumptions are related, for example, to the dimension of the problem. So I don't know if this approach is okay if you have a one-dimensional parameter space, but I don't know how it scales with the dimension of the parameter set. Anna Delagnan has a very nice paper, actually, where he has the exact scaling with respect to the dimension. So it's for a version of the Langevin Monte Carlo algorithm. So it's very nice. I mentioned it as a preprint, but maybe it's accepted since I wrote this slide, so I don't know. But anyway, it's a very nice paper. On the other hand, you have many assumptions on the pseudo-posterior in this paper. So here I want to discuss another possible approach. Okay. So the idea is not to use Monte Carlo methods at all, and to use optimization theory. Okay, you convinced me it's the best thing to do. So the idea is, well, I mean, just for one slide, I will use this notation, which is the usual notation for the posterior in Bayesian statistics. Okay, and the idea is just that, well, if this is not reachable in practice, let's not try to reach it. Let's try to reach a simpler object. Okay, so what we're going to do is to propose not to how can I say, to pay attention to all the possible aggregation distribution, but to pay attention just to a fixed family of aggregation distribution. For example, a parametric family, like all the Gaussian distribution, okay? And then we are trying to minimize over this family the distance between what would be the true posterior or pseudo-posterior, so our objective, and the approximation. So actually, this is not our idea. Obviously, it's very famous in Bayesian statistics. People use it since a long time. So I don't know actually what was the seminal paper for this idea called Variational Bayes approximation. But I learned it in papers by Michael Jordan on application to graphical models. But I think it was one of the first to use this method. I'm not sure, but
I think like mean field was used like one subversion has been used like for a long time.
Okay.
I don't know who coined the name.
Like it's statistical.
But when I say who is the first to use this, I mean who is the first in statistics, because if we rediscover it in our own field, usually we don't pay attention to what was done before in other fields. So it's no, okay, you're right. Probably you're right. It should have been used in physics much before.
I like the Jordan reference.
No, this is why I used it. No, I mean, it's true. I learned it in this paper myself, but probably this paper provides more references to what was done before. So in the end, the thing is that, okay, you use either a non-parametric or parametric family. So by this, I mean finite or infinite dimensional set F. So the mean field approximation would be the case of usually an infinite dimensional set F. But here we focus on a parametric approximation. So you just give a set of probability distribution rho that is indexed by a parameter A in a finite dimensional space. And then in this case, you completely replace your posterior sampling problem or your posterior mean problem by just an optimization problem. Okay. So actually it's done. I mean, in some sense, I'm going to present now applications. I'm going to try to, obviously, to justify this approach and to prove using the previous theory that actually, in some cases, you don't lose a lot in your prediction ability. But I mean, don't expect me to provide, for example, optimal approximation optimization algorithm here. Okay, it's not my job. I'm trying to learn it, thanks to your talks yesterday and today. But I'm not the one who can give the best, in any case, the best possible algorithm here. I just want to show you that actually, even if you use aggregation theory, the problem can boil down to an optimization problem, which you can solve. Okay. So our first question was, do we have any theoretical guarantees on the approximation? Okay. So I will present the result, but just before a few explanations. So this is what we target. This is what I want to compute. So I want to minimize the distance in terms of Kullback divergence between the approximation and this pseudo-likelihood. And the thing is that, and this is exactly what you said before, Francis, when you write it, it boils down to the aggregated version of the empirical risk this time, plus the Kullback divergence, and you have a reminder term, but actually it does not depend on A, so I can forget about it when I'm doing minimization, okay? So actually what I'm going to do is first to minimize this with respect to A, and then define A as my estimator, and finally my aggregation distribution. If it's necessary to compute it, then it's actually rho, where you take the parameter alpha, A, sorry. Yeah?
So I'm a bit confused why you want to approximate this one instead of just the bound you have actually used to derive this one.
Actually, it's the same.
Okay, so it doesn't change.
You will see that actually the bond that I had, sorry, where is it? The bond that, and this is actually why we had the idea to do this and to look at variational algorithm. Is the thing that is the bond, well, it's too far away in the first slide, but the bond that we had on the aggregation procedure, actually its proof is based on the fact that we minimize this bond with respect to all the probability distributions. While actually, if you just minimize over a parametric state, it still gives you a theoretical guarantee on what you get in the end.
So you're saying that the KL between distribution was the right metric of distance to minimize the bound? That's what you're saying?
Well,
My point is you had a bound which was actually giving you the actual performance you cared about, which had nothing to do with KL in general. It's just like the risk. And so you just want to find a new approximate aggregation measure which has good risk, right? So why minimizing the KL?
Okay, so I have two answers for this. I mean, first, some people did it before, and obviously if you try to replace the KL by another metric on probability distributions, things might be harder from a computational point of view. I mean, the good point with KL is that in the end you can compute it explicitly. So, I mean, you can have, you know what you want to minimize. I mean, if you replace it, for example, by the total variation measure, I'm not sure that you will be able to say anything about how to minimize this. So, the reason why we were interested in this is that actually, the minimizer of this quantity, it plugs in very easily into the analysis that I presented before, okay? So these packed Bayesian bounds that were already known, where you relate the prediction risk actually to this balance between aggregation and distance, I mean Kullback-Leibler the distance with respect to the prior, then actually you can plug this into this analysis and get a theoretical guarantee on your approximation. You see what I mean, or no?
This is, your bound is essentially that one with
Exactly.
R replaced by capital R.
Exactly. You can get you just guess the next slide. So I'm going to show the next slide now.
So okay, just I read your paper, so I'm not guessing. It's just like for
No. My explanation was so good that you guessed. I know. Okay, I mean, so in some case, I mean, these results, I mean, I wanted to cite the paper, obviously, but I shouldn't be proud of it in some sense, because it's just weakening a result that was existing before. But what I'm, in some way, more proud of is what will follow, the fact that actually it leads to a practical procedure for aggregation, okay? So this paper that also, okay, I forgot to mention my co-authors at the beginning of the talk, so now it's time. It's the paper that we wrote with Nicolas Chopin and James Ridgway. James was a PhD student of Nicolas at NSA, but now he's doing a postdoc in Bristol, okay? And it tells you that actually, if you use this variational approximation, so rho tilde, it's not the rho hats that I had before, sorry about the mess, but actually rho tilde is this one, the one where you plug the minimizer of this criterion, okay? And the approximation that you have then, instead of having the best balance, okay, for between risk and KL for all the probability measures, then you have it for only in the family A, okay, only in the parametric approximation. Obviously, you can do it for non-parametric approximation like mean field. Actually, we did it in the paper, but as this is only a 3-hour talk, I just wanted to present the short version, okay? So the thing is that obviously the work is not done then. I mean, you have a bound, it looks in an abstract form. The question is, I mean, do we have, and actually, obviously, if you take here a very poor family A, it's possible that this bound is very large, okay? So the thing is, now, it does not give you a way to prove that VB, variational-based approximation, always works. It provides you a way to checking when it works. I mean, you have this bound, you compute this bound in your model. If you get something that is good, then it means that to use VB, you will not lose anything in terms of accuracy when you use it for prediction. On the other hand, if you compute this bound and you find something large, it just tells you nothing, okay? So it's just a tool to try to make sure that the VB approximation makes sense.
It's the same with variational inference. If it works, you're happy. If it doesn't, you don't know, you can't say much.
Yeah. But some way it kind of gives you a theoretical guarantees, at least in some setting it should work. Okay, so I prepared the proof of these results. So I mean, I'm not sure. Maybe I should first present the applications and then go back to the proof if I have time later. So, okay, so I want to apply this to a linear classification problem. Okay, so in the batch setting actually. So I come back to this setting. Okay, so you have a sample IID from P. Sorry. Then this time classifiers are linear classifiers. Okay, so you just compute the scalar product between the object and a parameter, and then you check on what side of the hyperplane is your object. The risk is actually then in this case the classification risk, the probability to make a prediction error, and I want to approximate it by the empirical risk. So as thanks to you, I learned a lot about optimization theory. I can try to minimize this. So I just have to compute the gradient of this quantity and set it to 0. I think it's always work in order to make approximation and to make optimization. But I mean, in this case, I was not able to compute a sensible gradient. So actually, I decided to use our approach with aggregation. So I use a Gaussian prior just because it was simple for calculations. Actually, I will explain what can be changed if you replace this by another prior if I have time. But for the moment, just stick to a Gaussian prior. And then, actually, so what is going to be the posterior? I mean, the posterior is the prior multiplied by e to the minus this. Okay? So it's not very nice. And the idea was just to approximate it by a Gaussian distribution. Okay? Which must be quite easier, and in some sense, then you just have to optimize with respect to mu and with respect to sigma, and you hope that in the end you will get something sensible. So first, what is the optimization criterion? In this case, we wanted to write that down explicitly, and in the end, what you obtain is this. So actually, phi is the CDF of the Gaussian distribution, and you obtain something that obviously, well, actually, this looks like a slightly modified version of the empirical risk. A smooth version of the empirical risk. It's due to the integration with respect to the posterior, to the aggregation distribution. Then you have the mu squared term, so it's like a ridge penalty. And then you have also this penalty depending on the on the covariance matrix. Okay. So the problem is that, well, in some way it looks better than this one in the sense that this is a smooth minimization program, while this one was not smooth. On the other hand, it's still not very good in the sense that it is not convex. And I heard in the talk yesterday that you have to use the word convex a lot when you talk about optimizations. This is another thing about optimization that I know, so it's not so good. Even though we tried to optimize it, I mean, in small dimension, you can still do it, using, for example, gradient descent, but at different scales, so using deterministic annealing. And yeah, sorry, first I should show you the results, maybe, before the theoretical analysis. But okay, so what we did here, we took 7 data sets on the machine learning repository. We used sequential Monte Carlo, which, I mean, it's a Monte Carlo method that works well, at least when the dimension is not too large, you know that it will give you a kind of benchmark result. We compared our variational approach in this case, and then just as, how can I say, we used a non-linear SVM to compare to linear methods just I mean, I didn't know why we did that exactly, but the reason was that we wanted to use another method and check for the data set whether, I mean, it's sensible in some way to analyze it using a linear method or not. I mean, for example, in this case, you see that the two linear methods, they don't perform so well, and in this case, it's clear that you should use a non-linear method. On the other hand, in this data set, well, it seems that to use a non-parametric method like SVM does not bring you a lot when compared to linear methods. So in this case, linear classification is sensible. And you see that in many examples, actually, not in all the examples, not here, for example, but in many examples, we have actually a slightly better performance, which is due to the fact, yes?
What is SMC?
Sequential Monte Carlo.
Yeah, but what on which model? Same model?
Oh yeah, on the same model. Yes. So sorry. So actually, it's the approximation of the usual pseudo-posterior using this. Okay. So actually, we just tried to did what we would have done before we learned about optimization. Exactly. It's not MCMC actually, SMC. It's a variant because actually it's this algorithm where you generate a point from the prior, and then you just eliminate those that have a poor posterior, but the ones that have a large posterior, you duplicate them and then apply to each of them. Exactly.
Oh, it's another name for particle filtering.
Exactly. It's yeah.
So the two columns are the same.
The same estimator computed in two different ways. And the one that I'm trying to sell today is this one, and this is the old-fashioned one.
Like VB is superior to Monte Carlo?
I'm not saying that it is superior to.
You just said that like 1 minute ago.
Okay, I say that I'm trying. I say that I'm trying to sell VB today. So obviously, I mean, I chose the 7 datasets that prove that I'm right, and I just add this one because I know that in simulation study, you don't have to be right 100% of the time. No, I mean.
Why do you say your aggregation methods are linear? If you're aggregating different linear classifier anyway, that's non-linear, no?
Yes, you're right. That's non-linear in the end, but it uses a linear set of predictors.
Yeah, but at the end, it's a non-linear predictor.
You're right. Okay, but even though, okay, my objective in the end, and using this bond that I will present later, I mean, I might be much better than the best linear classifier, but actually my theoretical analysis just says that I do as well as the best linear classifier. I will come back to this later. So actually, in some way, this was my objective. My objective when defining a set of linear predictors was to do as well as the best of them. It's true that when you aggregate, you can do much better than this, but even though this is not what we tried to do in this analysis, okay, so, and actually in this case, obviously, I mean, this improvement might be due to the clear non-linearity of this. But I mean, for example, in this case where clearly it seems that there is a very good linear classifier, you still have an improvement, and which was due, from what we observed, actually, to the fact that, well, obviously we stopped SMC after some time, and you're not sure that it converged, while actually we stopped the gradient algorithm when the gradient was exactly equal to 0, and so we were sure that it converged.
Exactly equal?
Yeah, actually, up to 0.5 decimals.
Yes. But didn't you say it was non-convex?
Yeah, no, you're right. I mean, it's not convex, and I will discuss it. Promise. I mean, I pointed this out exactly. It's not convex, so I pointed this out. We don't have guarantees on the minimizers, but I will come back to this later. I have another bond later, actually. So, but first, okay, before this, so we have these results that seems, well, at least promising, even though we have to say more. Yeah.
So this is the final performance. Could you plot as well the bound that you obtain? Because for me, Pack Bayesian is used also to get like provable confidence bound of the predictions. Could you plot them? Did you plot them to see if they were like meaningful or?
No, I will. I mean, sorry, I don't have the plots here anyway. But I mean, you're right. And once again, I will come back to this later when I will discuss the proof. Just one thing now. Actually, if we use the theorem that I presented before, so sorry, where is it? Here, this one, and we replace this set A by what I said, okay, the set of linear predictors. Then we obtain here this result. Okay, this result. So what does it tell you? Well, there is an assumption. I will come back to this in 1 minute. But first, it tells you that the risk of your aggregated method. And actually, you see that here I use the randomized version. Okay, so you're right. I mean, it can be, if you're lucky, it can be better than linear. But anyway, what I know, at least for sure, is that I do as well as the best possible linear predictor, plus this rate square root of d over n, which is actually, once again, in classification, the best you can do. Well, there is an additional log terms, which can be removed at the cost of very, very exhausting analysis. But in some cases, it can be removed, actually, using Pack Bayesian bonds. But in the simpler version, you have this log n term, okay? And yes, I just wanted to mention this. So you have a kind of regularity assumption in some sense, which tells you that when you slightly change theta, the real risk doesn't jump a lot, which is obviously sensible in the sense that you replace a point estimator by an aggregated estimator that takes a neighborhood, and obviously it cannot work. I mean, if you use a Gaussian aggregation, it cannot work if you don't have just a kind of regularity. So you have this assumption, and if you don't have this assumption, we are not sure actually about what happens. Okay? I want to mention that this assumption is not necessary for the pack Bayesian analysis of the empirical rate aggregate if you're not doing VB. In this case, we have this assumption, but under this assumption, we know that the method will work. And actually, how do I prove this result? And this is the opportunity actually to show you another application of the trade-off between risk and KL term. Okay? So actually, what we do is that we just apply the theorem. So the risk of the aggregated predictor is actually as good as the infimum over all the possible Gaussian distributions. And actually, for the sake of simplicity, I used just the ones with a diagonal covariance matrix. But actually, you can change it. It will improve on the constants. But this makes life much simpler. Okay, and the idea, I don't derive all the calculations, but first, you know the Kullback divergence between two Gaussians. So in this case, it's this term. And you see that here you have the M, that is the dimension. So, sorry, here it's M, and in the previous slide it was D, but it's the same. So you have this term here. And then the other term, actually, this is where this kind of smoothness comes into account. So actually, the aggregated risk is almost as good as the risk of the mean of the distribution plus some remainder. Okay, and you just optimize with respect to everything with respect to this S squared here, and then with respect to lambda, and you get in the end the optimal bound. Okay, so this is how it works. Okay, I still have 15 minutes.
Yes. And how does this differ from the full Gibbs posterior?
The bound? Okay, actually, so in most of the papers that I know, when people wanted to use here to compute the bound for the full Gibbs posterior, they use here the infimum, and the first step of the bound was to replace the infimum by over all probability distribution by a reasonable parametric set anyway. So the bound is the same.
You mean okay, so when you apply the bound, you do this anyway.
Exactly. So this is where actually we had this idea. It was frustrating in some way to use VB approximation in the bound, but not for the estimator. And actually, obviously, you can do it. So this is what people do. In the beginning, they were not using actually Gaussian, but rather something like uniform distribution on the ball around the best parameter, which actually is a good idea because it allows you to use pack Bayesian bound to prove bounds on the empirical risk minimizer as well. But usually, as long as you have as it's possible to change the mean, to take whatever mean you want, and to change the scale of the distribution, you can basically get what you want. Okay? Yeah, sorry. So, as I told you before, it works well, but the problem is that obviously it's not convex, and so as it's not convex, you're not convinced. It's one of the jokes I prepared yesterday. Sorry. Okay, so obviously you know this. Now you're doing classification. You want to replace the 0-1 loss by a convex surrogate. So for example, you can use this paper by Tongzhang, in which you have many theorems about all the possible replacements for the 0-1 loss and what you lose in terms of rate of convergence. So for example, here we wanted to use the hinge loss. Okay, so the one that is used for support vector machines. Okay, so we define now our risk in this way, and we have this empirical risk, and we still use a Gaussian approximation for which this time, and this is important for the analysis actually, this time we fix the Gaussian approximation with just a fixed variance. Okay, all the coordinates have the same variance, and the covariance matrix is a diagonal one. In this case, we did the calculations, and the calculations are not very difficult, but what is not maybe obvious when you see it is that this is a convex criterion. Okay, so you have still the CDF of the Gaussian distribution. Here you have the density function of the distribution of this distribution. So here in the end you have two terms that still looks like a kind of actually it's just a convex surrogate. It's a new convex surrogate, and Sylvain pointed this to me last time. But this is just a new convex surrogate of the 0-1 loss function. But this is a new one for which you have another guarantee. Okay, so this will be the empirical risk. You still have this kind of ridge term here. Okay, so the penalty that is the square of the parameter mu, which is due actually to the Gaussian prior, and then the penalty on the variance. And well, it's not obvious. I mean, for example, we tried for fun to replace here the 0,1 loss by other convexified loss function. And then when you integrate with respect to the posterior, you don't necessarily get a convex criterion, okay? And actually what can be, I mean, usually it's convex with respect to mu, but what can be painful is the parameter sigma, okay? So in this case, we are lucky it's convex.
Convex in sigma?
Yeah.
How do you check that?
Just with a second derivative. We did the computation and it works. Okay, you read the paper.
Not up to that point.
Okay. I mean, no, it's not obvious. And once again, it's not something like, it's not because you take a convex loss and then you integrate that you will obtain a convex function. But then in this case, it works, okay? And then in this case, so this is where I told you that I took many precautions about that. I'm not a specialist of optimization theory. Well, in this case, there's not a lot that you can do because it's convex, but it's not really more than convex. You don't have many good properties. For example, you can, if you make some assumptions on sigma, like for example, if you prevent sigma from going too close to 0, then you can make better things. But in this case, we just like took a ball on the parameter set mu and sigma, and then use the gradient algorithm. But what we were proud of is that even though we don't know a lot about optimization theory, we were able to write this theorem, which tells you basically, under the same assumption as the previous one, that you have, I mean, at each step, okay, you compute, at each step of your gradient algorithm, you compute an aggregated distribution, so you have a mu at k and a sigma at k, and then the risk according to this procedure, so the risk according to what comes out of the computer and not what comes out of the paper, is actually as good as the best possible risk for a linear classifier, plus the minimax bound for the classification problem, square root of d over n, and plus something that depends, well, probably badly for people who are good in optimization theory, but still something that depends explicitly on the number of steps that you have. Okay, so obviously, I mean, what I wanted to present to you, and this is why I went into the details more than into a good bound in the end, is that obviously you can play with this. You can change the hypothesis, you can change the parameter class, the predictor class, you can change the prior, and then in the end you can change the algorithm, and I'm sure that you will be able to improve on this bound. But still now, you see that using pack-Bayesian bounds, it's possible to provide guarantees on the prediction that you have for variational approximations, and it's possible to reduce the problem to a convex optimization problem in some cases. Okay? I just wanted to advertise for something that, I mean, I feel free to advertise for it because it's not mine actually. Just after we submitted this paper, James Ridgway, so one of my co-authors, decided to write a package which after a very long peer review process is now available on our website. And well, I mean, I don't want to, I mean, it works like very basically, so I don't want to enter the details, but it's just that, I mean, you just enter obviously the matrix of labels and the matrix of objects. But the thing what I wanted to show is that even so I didn't make the plots, actually you can get the bound, okay. So for example, in this case, you know that the probability, with probability at least 99%, the probability of error is smaller than 0.79, which is not so good.
This is the bound on the hinge loss.
In this case, yes. This is the bound on the hinge loss. Yeah. But yeah, you're right. This is the empirical version on the bound on the hinge loss. Even though, okay, you're right. Even though it's not very good, I mean, we know that these bounds are pessimistic, and especially when you use it in a problem where you clearly have a linear classifier, then the square root d over n rate is not optimal. You can replace it by d over n when you have a margin condition or something. So this bound is usually not so good, but I mean, we are happy with the fact that to minimize this bound provides a good estimator. Okay, you can play. I mean, in some points, it's possible in the end to get something smaller than 1/2. You have to wait for a long time, but it's possible. Do I have time for the proofs, maybe? 5 minutes? Yeah, okay. So I come back to the main result. I mean, the proof is quite obvious, but I want to, I mean, it will be the opportunity to mention this empirical bound, which unfortunately I did not plot, but Okay, so sorry, I want to prove this theorem. So the fact that your approximation, your VB approximation performs as well as the best possible approximation in the parametric family A, okay? And then we start with Hövding's inequality, okay? So you just have a bound on the exponential, exponential moment capital R minus small r. And then, well, I just rewrote it introducing my probability epsilon, okay? And you integrate it. So this is the change, I mean, with respect to Vapnik's type bound, is that you integrate with respect to the prior, which does not change anything for epsilon, okay? Because it's a constant. And then, so this is very standard. But then you get actually to this point, okay? And then you use this lemma, I mean, the fact that you cannot, that you can compute the convex conjugate of the KL divergence, and that, moreover, what I will use that later, you know actually you know the distribution row that reaches the minimum here, okay, and the supremum, sorry, here. So actually, when you use this lemma, you get this kind of uniform version, uniformized version of Hövding's inequality, but here again, as I integrated with respect to the prior, the difference with what you have in Vapnik's type analysis is that in Vapnik analysis, you have a soup with respect to the parameters theta, while here you have a soup with respect to all the probability measures on the parameter set theta. Okay? And then finally, you use Markov's inequality, and it gives you this empirical bond. And I wanted to insist on this because actually Francis mentioned it many, many times, but here, you know that it's not only for the minimizer, it's for all possible probability distribution row, all possible aggregation distribution. Then the risk of the aggregated procedure is smaller than something that is completely empirical. I mean, it depends only on things that you know, the risk, the empirical risk, so it depends on the sample, and then the parameter lambda that you choose, and then the Kullback divergence with respect to the prior that you choose as well. So actually, you can compute this bound numerically, and this is the bound that is provided as well by the package, okay? So actually, I mentioned in the beginning of the talk the origins of Pack-Bayesian bounds, like McAllister work. He focused mainly on this kind of bound because he thinks that's what's important in the end, to be sure that your classifier with probability 99% has a mistake that is smaller than 0.1, okay? On the other hand, even though if you want to prove something, a theoretical bound, something that depends on the true prediction risk, you have to derive this as a tool anyway, so. This is quite important. Yes?
That one, are you allowed to optimize over lambda?
No, you're not allowed to optimize on lambda in this bound. Okay. On the other hand, I mean, you're allowed to, in some way, you're allowed to optimize on lambda, but for a lambda that does not depend on the sample. Okay. On the other hand, what you can do is to use the union bound, obviously, for lambda on the grid, and then actually using the fact that this is increasing and this is decreasing with respect to lambda, you can even, optimize in an interval, and this is what people do actually. Well, I mean, usually they provide a more sophisticated version of this bound where you have the infimum with respect to lambda, even though it's not the thing that works in practice. I mean, in practice, if you want to choose lambda, it's the main problem that we have to solve yet. Because the minimization, even if you would minimize this bound with respect to lambda, usually you don't have the best possible lambda. And cross-validation, for example, performs much better, but obviously it's much, much expensive. Okay, so you have this empirical bound, and actually the thing is that the reason why people use this exponentially weighted aggregate that I introduced in the beginning is that actually this is the one that minimizes the right-hand side, okay? And as it minimizes the right-hand side, you have here an infimum, and then what you do, well, first still you have this empirical bound, okay, that I mentioned before, but as you minimize the right-hand side, what you can do is then to use the reverse bound, okay, when you replace you start again all the process, but you replace r minus small r by the opposite of this. And then actually, what it tells you is that you have this time something which seems useless in practice. Okay, the integral of the empirical risk is smaller than the integral of the true risk plus something. But you can plug it in the previous analysis. Okay, so what we had before, the integral of the, minimizer is smaller here than the empirical bound. But the empirical bound, if you take the minimizer, it's an infimum. And then using this result, you can replace the empirical risk by the true risk in the infimum. Okay? And so here you have the theorem. So this is quite a standard analysis, actually. But the only point was to remark that actually here, I mean, if you don't minimize with respect to all the probability distribution, but just over your approximation family, then it still works. Okay, well, it's time to conclude. So I have just one slide called conclusion, I think. Yes. So there are other things to do, and actually some of them are already done. In the paper, we also provide, for example, complete analysis of ranking models. So it's very similar, obviously, to classification because we still use linear score functions, but we also have the same thing, actually, that we are able to replace MCMC methods by optimization method, and even in some cases by convex optimization problems. We also have a sketch of the analysis in matrix factorization. I mean, a sketch of the analysis in the sense that there are many problems there. In the sense that, yeah, if I have just one more minute, I will come back to this. Sorry, this result. Sorry, yeah. This result tells you that the variational-based approximation performs as well as, in some sense, as the exponentially weighted aggregate that you wanted in the beginning, if this term is not too large. So actually what we did was to prove in this case that this bound, whether you compute it for the exponentially weighted aggregate or for the variational approximation that is used in practice by people, by Bayesian statisticians when they do matrix factorization, the bound is the same. Okay? So it means that in some way, if the packed Bayesian bound would hold for the exponentially weighted aggregate, then it would hold for the variational approximation as well. On the other hand, up to my knowledge, until now, nobody was able to prove that it holds for the exponentially weighted aggregate. So there is a missing part in this problem, and obviously there is the other missing part that is that the criterion used anyway for matrix factorization are non-convex, and so we don't know whether we converge actually to a proper minimum or even to a minimum at all. But even though, I mean, it seems that there is something to be done there, even though we are not able to complete the analysis. Okay, so the theory is not complete. I wrote it. We have other works in progress, actually. So James is currently, I mean, in the package for the moment, we only have one version of the gradient descent, which is not actually necessarily the most efficient one. So actually, James is currently writing other functions to use other optimization methods. And actually, what I'm interested in currently, and this will be my last slide, it's a question for you. Can you help me on this? You remember that I presented in the beginning two packed Bayesian bounds, one for the batch setting and the other one for the online setting. And the one for the batch setting, actually, it holds for the exponentially weighted aggregate, but it also holds for the variational approximation. I say nothing about optimization, I mean, about the online bound. And the reason why is that we were not able to perform the same analysis. So I can show you what we have. Remember that in this case, at each step t, you want to compute the mean according to this probability distribution. And what you could do, I mean, is to use a VB approximation, so you perform optimization. It will be already more costful, actually, than a proper online gradient algorithm, because here, at each step, you would have to perform an online optimization. But even though we're not really sure that this one works, okay? If you use this, okay, so the mean according to the mean prediction according to the the approximated posterior, sorry, rather than the true one, then actually we have this bound. Okay, so we have the cumulated loss that is smaller than the same criterion as the one that you would have for EWA, but on the class. But in this case, you have an approximation term, but instead of having it only once, then actually you have it at each step of the algorithm. Okay, so it means that the cost is much, much higher. So maybe actually, I mean, obviously, this is what comes out of the standard proof for online EWA. Maybe there's a better way to analyze it, but until now, okay, we were not able to improve on the fact that we don't pay the price for the approximation once. We pay it at each step of the algorithm. And so, I mean, if there is a non-zero distance between, in some way, the true EWA and your approximation family, then you might pay a huge price here. So we're not able to generalize this analysis in online prediction, but we would like to. So if you have some ideas, and if you want to write a paper for me, then you're more than welcome. Okay, so I mean, I can start to work on the jokes for the talk that we will give about that later. Okay, so thank you for your attention. And
okay, thank you, Pierre. Is there any questions? Yes.
I was wondering about the connection. I mean, you gave a lot of citations and you didn't cite that work, so maybe you were aware of it. But so I was wondering the connection with the work that Tony Guevara did on maximum entropy, what he called maximum entropy discrimination. So he considered something which is fairly similar to what you're doing with the hinge loss. Essentially, a formulation where you compute an expected value of the empirical risk, and you replace the regularization term by a Kullback-Leibler divergence between a distribution on the parameters, I forgot how you call them, and a certain prior distribution. So it seems very related to this. Do you know about this work? And
No, but I'm very interested by the reference, so obviously I will read this paper this afternoon, tonight after the talks. Yeah, no, really, I mean, I'm interested in it, but I didn't know it.
I think it dates back from 1999, so I think the connection with Pack Base is not as elegant as what you're presenting, but I think it's related.
Okay, thanks.
Yes.
John Taylor and Langford proposed already Pack Bayesian bound for linear classifier. I would like to know if you know this work, and
Yes.
can you comment on the relation between?
Once again, I mean, I think that we have different objectives because usually they are more interested in the empirical version of the bound. So something like this, when you relate, I mean, you provide an explicit bound for the. But I mean, it's true. I mean, in some way, Pack Bayesian bounds, once again, you have to minimize with respect to an infinite dimensional object, and people already had the idea to minimize just over a smaller set of parameters. Okay, so it just, I mean, I read this. The thing was to make a connection with VB, but.
Yeah, but I think at the end the algorithm is very similar to some algorithm already existing in Pack Bayesian literature, especially the first one proposed with the Gaussian posterior, the univariate Gaussian posterior.
Yeah, once again, I mean, I don't claim that any of the algorithms here are new. I mean, the thing was just to provide an analysis of existing algorithm. But you're right, I mean, most of the algorithm already existed before anyway. Yeah, we know about this work by John Taylor, yeah.
So did you run the SGD version on the hinge loss version on the experiments? Like you had 3 columns where VB was doing better than
Yes.
Sequential Monte Carlo.
Actually, James did it, and this is the version that is implemented in the package.
So it's the
Yeah, sorry. So actually, sorry, I removed this slide actually because okay. I thought I had it somewhere. Yeah, you're right. Actually, sorry. Where is it? I'm lost. Yeah, we had this, and we have another one in the paper with the hinge loss version. So actually, usually, I mean, in most cases, I would say, I can't remember exactly, maybe 5 or 6 cases, it improves on VB in the sense that it converges much faster. But there is one case where we have a very, very surprising accident. I don't know why. We did not understand it. But in much cases, it works much better than this one. So.
Well, much better, and like there's a difference between speed and test error. So.
Exactly, but I mean, in some way, the idea was I mean, this is a test error, okay? It works much better than in the sense that if we run the algorithm for the same time, then in the end, we have a better test error. Okay, in some sense, the idea of this simulation study was that we didn't want to split between the optimization and the test error, but that we wanted in the end a good test error, whatever you have, in the sense that you can have a complicated model with a poor optimization procedure or a simple model with a good optimization procedure. In the end, we want to compete in the test error level, obviously. So, I mean, the improvement that we have is in the test error in the end, but obviously it's due to a better optimization.
But to be clear, this column of VB there was with the original multivariate Gaussian approximation.
Yes.
And then you get a local minimum by setting a gradient because
Yes.
it's non-convex, right? And you're saying if you compare that with the other one, which is now using not a multivariate but a univariate, well, I guess identity covariance matrix, but it's the hinge loss it's looking at.
Yes.
Now it's convex.
Yes.
Now you're saying between those two, they gave the same test error, but one much faster.
They gave this actually even a slightly better test error in some cases. I mean, I don't know why, but actually you're right. I mean, it might be that the accident that we have, I can't remember for which Probably it's for this one, I think, which seems very easy in some way, and then actually we have an accident in the sense that it's the worst method, and it might be due to the fact that actually we have to restrict our attention to diagonal variance matrix. I don't know, but yeah, in this case we don't have a good prediction error. But yeah, what I wrote there is the prediction error. It's the test error on the half of the sample. Yeah.
Okay, another question?
You mentioned that integrating a convex function is not necessarily convex, but how about integrating a strongly convex function?
I don't know. Is there something obvious or?
The complexity in sigma is never obvious.
Exactly. I think that's the problem because when you integrate a convex, instead of the 0-1 loss, you integrate a convex loss function with respect to theta, it's okay. But the problem is that the criterion also depends on the Kullback divergence. And the Kullback divergence, I mean, you're already lucky if it depends in the convex way in sigma. You see what I mean? I mean, the criterion, sorry, I should. When you minimize this, okay, if R is convex, you integrate with respect to a probability distribution. I mean, this should be convex as well, but the question is this part convex? And with respect to sigma, it's not always the case.
But even the integration of the loss, why should it be convex in the variance parameter?
No, you're right.
Okay, so I suggest to thank the speakers of this morning.